Hi everyone, welcome to the fourth lesson for topic 4.3 Networks and Decision Mathematics. We are still under the subtopic of flow networks and we are going to continue our discussion in maximum flow. So I hope that by this time you have been quite familiar with how to use the systematic approach to find out what is the maximum flow given a flow network to you. So for today's lesson, we are going to look at the part where what is that meant by the theorem of maximum flow and minimum cut, and how are we going to use minimum cut to verify whether the flow that we get is it a maximum or not. Alright, so we will start off with what is that meant by cut, how to calculate, how to identify the capacity of the cut. Then after that, we'll be talking about the theorem and we are going to do some question together relating to our previous example in our third lesson. Alright, so let's start with the introduction on the definition for a cut. Alright, so I'll start off with introducing to you what a cut is. So in a flow network, a cut is a partition, or you can say that it's like a slice as well. So it's like a partition or a slice that separates the flow network into two separate groups, which you have source in one group, which means where all your arcs starting from, and also you have sink in the other group, which where all the arcs going to. So the main thing for cut is that a cut will disconnect all the source from the sink. Or you can also say that it connects the sink from the source. It's just the same thing, right? Alright, so I'm going to show you how a cut look like and what is that meant by a valid cut and invalid cut. Invalid cut meaning that this cut is not valid because you didn't disconnect the source from the sink. Alright, so let's try to look at how a valid cut look like. For example, if I try to draw a line like this, alright, so again, it is not necessary to be a curve, so you can even just draw a simple straight line like this as well. Alright, so it depends on your own preference. So as long as make sure that the cut that you are putting, they always cut through the edges only. So there's no something that looks like this. Alright, so the cut through the edges only. It doesn't pass through the vertices. Alright, so for example, this is a cut. Alright, so what can you realize here is that it divide your flow network into two groups. So you have one group with the source here and your sink is in the other group. Alright, so that's why this is a valid cut. Because after I cut it, then you can realize that this flow, you cannot flow from A to B already. Then after that, you also cannot flow through the flow cannot go through the edge AC as well. So that's why there's none of the flow will be able to go from the source to the sink. So this is what is that meant by the cut disconnect the source from the sink. Alright, so a cut can maybe also like this. Alright, so this is a valid cut as well, right? Because you have the source in one group, then after that you have the sink in the other region. So which means that you are having your source in one region, then the other region you are having a sink. And then you realize that after you draw this cut, then which means that the flow cannot pass through the HBD, cannot pass through the HCD. So that's why there's none of the flow can actually reach sink from the source. So this is a valid cut as well. Okay, so it can be something special even like this. Alright, so when you try to look at this line, then you can see that you are separating the graph into two regions as well. So this is one region and this is another region. And the source and the sink is not in the same region, right? So that's why the first one is correct. Then also when you try to check it out, so if let's say there's none of the flow can pass through AB, alright, then after that, none of the flow can pass through CB and also CD, then which means that you are disconnecting the source from the sink as well. So this is one of the valid cut also. So even you can try to draw like this is a valid cut as well because you have one region with source and another region with sink. Alright, so just like that, I think that's the maximum number of cuts that you can have in this graph already. Alright, so now let's try to see some example of invalid cuts so you can understand that what is that meant by you can't separate your source and sink. For example, if let's say I draw a cut like this. So what you can realize, this is one region and this is another region. So source and sink falls under the same region. So that's why this cut doesn't separate your flow network into two separate regions, which with source at one side and sink at one side. So that's why this is an invalid cut. All right. And also you can try to understand it in this in the perspective of this cut doesn't disconnect the source from the sink, because even you try to make a cut here, but you still the flow can actually go through AC and also CD, and you still reach the sink from the source. Am I right? So that's why this cut is an invalid cut, because it doesn't stop every flow flowing from the source to the sink. Okay, so similarly, this is a valid cut as well, because you have one region here and another region, source and sink together. So you cannot also draw something like, okay, let me try to see whether we have another idea. Okay, this is still a valid cut, or it's the same thing like what we have just now. Yeah, so this is like that example for a valid cut lah. Maybe you also want to ask, can you draw like this? So if you draw like this, then the same thing, you not even separate it into two groups, right? So these are all under the same region as well. So that's why this is not a valid cut also. All right. Okay, so I hope that you get an idea what a cut is and how to identify whether this cut is valid or not. So first thing, by looking at, normally if you satisfy the first one, then second one, of course you will satisfy it already. But then it will be good for you to understand what a cut does lah. So the first one, you'll be able to separate the graph into two separate regions with source at one region, sink at one region. So your source and sink cannot fall under the same region. Second thing, when you are drawing your cut, you must make sure that there's none of the flow can flow through from the source to the sink already. So the cut will disconnect all the flow from the source to the sink. Alright, so that's the part on the definition for a cut. So now we'll be looking at how to calculate the capacity of a cut and what is that meant by the capacity of the cut. Alright, the capacity of the cut is the sum of the capacity of the cut edges directed from source to sink. So previously we know that in a flow network, the flow always flow from the source to the sink, right? So there will be no, none of the flow will actually go from the sink to the source. It will be like in the opposite direction already. So when you are calculating the capacity, make sure that you only take those edges, those weights that directed from the source to the sink. So all the cut edges that directed from sink to source will be ignored. Alright, because it doesn't really contribute to the flow of the network. Alright, so or later when I try to explain it, then you'll understand it better. Okay, so we will be learning how to calculate the capacity for the cut. Okay, for example, this is our cut for this flow network. Alright, so you are going to look at what are the edges that this cut actually goes through. So of course, it's very obvious. So this cut pass through the edge AB and also AC. So that's why the capacity of this cut is going to be 6 plus 3. So just like that. So which means the capacity of this cut is going to be 6 plus 3, which is equals to 9. Alright, so you can see that when you are looking at AB and AC, they are both directing the flow from the source to the sink. Alright, it's not that B is your sink, it's that the source is under this region, right? Then the sink is under this region. So which means that you can see that these edges is actually from a source region to a sink region. So that's why it is capacity that you want to total up together. So the same thing, A to C, from the source region to the sink region as well. So that's why 6 plus 3 is going to be the capacity of this cut. Alright, the other way of thinking about it is to think that when you are calculating the capacity of the cut, it's basically calculating how much of the flow that you are stopping from the source to the sink. So definitely you can see that when you cut through this thing, right, AB is going to be the flow that you actually stop. So that's why 6. So if let's say you try to stop here, then flow can still pass through here, right? So that's why the cut, when you cut through here, then which means you stop the tree as well. So that's why the total capacity of flow that you actually stop by using this edge is 6 plus 3. So that's why the total is 9. Alright, so let's try to do another easier one first. So this one. So you can see that this is your source region and this is your sink region. So you can see that when you are calculating the capacity of this cut, then it will be BD, because the B here is at the source region, then D is at the sink region. So that's why the capacity that you are stopping is actually 7. Then the 8 as well, because if water cannot flow through here, you can still flow through here, right? Then so that you also need to stop the 8 here. So that's why it's from a source region to a sink region as well. So we need to calculate that. So 8 plus 7, which gives us 15. Alright, so I hope things are clear now. So you can definitely see that when you are trying to draw this curve, then which means that you are stopping the flow of 7 and 8 that directed from the source to the sink. Alright, so now we'll be looking something that is much more challenging and slightly tricky here. So this is why you need to understand that we only calculate those cut edges that directed from the source to the sink only. Alright, so let's try to understand this by using the idea for the region first. Alright, so as you see, this is the cut that we have. Okay, first thing, let's try to check AC. So A is in the source region, then C is in the sink region. So that's why AC here, you need to add up. Alright, next one, you can see that the next cut edges is actually BC, right? So you can see that the arrow is actually from C to B. So what you can realize is that C is at the sink region, B is at the source region. So that's why this direction, you are actually directed from the sink to the source, which is actually not, which is not valid in this flow network. Am I right? Because flow cannot go from a sink to a source. So that's why 4 is not what we want. So it doesn't really contribute to our flow of network here. So that's why we are not adding 4. Alright, next part. So when you look at B to D, so B is in the source region, D is in the sink region. So that's why, yes, we calculate 7. So the total is 10. Alright, I'll try to explain it with the other idea from by mentioning what I mentioned previously, which I say that you also can understand it by thinking about what is the capacity that you actually stop, right? Okay, so try to imagine like this. Now, this is your source, right? So water flow in here. So you can imagine when water flows in here, and then there's already a cut here, which means that there's no water flowing into here already. Am I right? So if let's say there's no water here, then which means that actually there's no water flowing into here. So that's why the edges here actually didn't stop anything, because that all the current, all the flow already stopped by this cut here already. So this cut here actually doesn't stop anything because you have no flow here actually. So the same thing, water flow through here and water flow through here, right? So that's why the cut here, you actually stop the flow flowing from B to D. So that's why the flow that you actually stop is actually 3 plus 7 only. Alright, so I hope that you get the idea why we don't involve 4 by using either you thinking of from a perspective of you cannot flow from sink to source. So that's the first one. Second one, you can try to imagine like how the flow works. So if you already stop at here, which means there's no flow going into here. So which means that the cut here is actually not important because it doesn't stop anything. Alright, so let's try to look at the next one. Okay, so this is the other cut. Okay, so let's try to check it out. So for the first cut here is is cutting through AB, right? So A in the source region, B in the sink region, so that's why 6. Alright, so next part is BC here. So you can see that C is in the source region, B is in the sink region. So that's why it's a valid one that we need to calculate. Alright, then the same thing, the other one is at here. So it's the edge C to D. So C is in the source region, D is in the sink region. So that's why it's valid. So 8. So that's why 18. Alright, so we can try to understand also from the flow. Okay, so again, thinking about water flowing in here, so that's why you stop here, right? So this is that is something that you're actually stopping, so 6. So same thing, water flow in here, water flow in here, water flow in here. So that's why 4 is valid and it is valid. So that's why 3 of them, you need to total up them together. Alright, so I hope that you can get the idea where how do you calculate the capacity of a cut. So this is very important. If you don't know how to calculate the capacity, right, then later you cannot do the minimum cut already, because this is the basic of it. You are going to use the minimum capacity to help you to solve some problem. So make sure that you understand everything here before you move on, okay? So if let's say you are feeling a little bit confused, so just try to repeat the video again and listen to the explanation again. All right, so now we'll be looking at the part where you see, right, from what we did just now. So this is like the 4 different cuts that we have for these networks lah. All right, so since there are different cuts with different capacity that we try to find, so you can see this is 9, 10, 15, and 18, right? So what is actually the significance of this? So if we can actually find out the maximum flow by using the systematic approach, then why do we actually need this minimum cut? All right, so before we move on to that part, let's try to identify what is the maximum flow for this network. All right, I hope I still remember how to do that. So from top to bottom, then you try to identify a path. Then after that, write down what is the maximum that you can pass through all the edges. All right, so the first one that we are having is ABD. So from top, right? So ABD, so here you can, the capacity here is 6 and 7. So that's why that's going to be exact 6 to pass through everything. So 6, so the flow here is 6, so you use up all the capacity already. The flow here is 6, so that's why you still have 1 here. Okay, so we continue for this part. So ACBD, I think for this case, it actually doesn't matter, because whether you go through here or you go through here, you are going to spend the total of 3 here lah. All right, so that's why I'm just going to go from a very logical, a common sense way, yeah. So I'm trying to skip the CB part. Okay, so ACD is going to be another 3. All right, so it doesn't matter whether you go through here or not. It's just that whether you want to use this or not, but the last answer will be always 9. All right, so this is the maximum flow that you can get. Let's try to write down our answer. All right, so you left with 5, and actually you cannot do anything already because here is all 0 already, right? Okay, so the maximum flow here is 9. Do you identify that something that's similar? So you can see that from our minimum cut just now, from all our cuts just now, the minimum that you are having is also 9. So this is not a coincidence. So you might want to just remember now, when we have the maximum flow value will eventually equal to the minimum cut in our flow network. So what I mean as minimum is that 9, 15, 10, and 18. So this is the smallest cut that we can find. So your smallest cut will always equal to the maximum flow. All right, so I'm going to explain it in a much more detailed way, and let's try to look at the part for maximum flow minimum cut theorem. All right, so the maximum flow minimum cut theorem tells us that in a flow network, the maximum flow from the source to the sink is equal to the capacity of the minimum cut. All right, so in everyday language, the minimum cut actually involves the process of identifying what is the bottleneck for your system. Okay, let me try to explain it like this. All right, so we use a very simple example, so you can try to imagine when you are drinking what is that called? You're drinking carbonated drink, right? So you have this bottle. Okay, so or you can try to think of like a container containing of water lah. Okay, so you have this much of water, so maybe you try to imagine that in every bottle here you have maybe 50 ml of water inside your bottle. Okay, so can you try to imagine if let's say you try to turn around this bottle, then you let the water to pour out from this bottle, right? Do you think that the rate or the time that you need for every single bottle to pour out all the water will be the same? Okay, let's try not to talk about the last one first. So let's go from the easy one, which is the first and the second one. So again, let me rephrase my word. You have the same amount of water in your bottle. So when you try to flip it around and you try to let the water to go out from this bottle, do you think that the time that you need to finish off pouring out the water will be the same? So when I try to imagine it, then you can understand that the answer is no. So reason being is, if let's say you are having a bottle with a neck or with like an opening which is a smaller one, a narrower one, compared to a broader one, it's going to, I mean, the water need more time to actually come up. Am I right? So this is a very common sense. I doesn't really need to, explain it by using any scientific way. So you can just try to, yeah, take a bottle and okay, just do a very simple thing. So you try to take a bottle and take a cup. So normally a cup, you'll have a wider mouth, right? So that's why when you put in the same amount of water, then you try to pour them out, then you realize that you need more time to let the water to come up from the bottle will normally, sorry, you need more time to let the water to come out from a bottle instead of you are just pouring out everything from the cup. All right, I hope that you get what I mean. So that's why you can imagine that what is the maximum capacity, maximum flow that I actually allow water to actually come out from this thing is actually determined by what is the most restrictive part. So same thing here. If let's say you have this very fancy pattern of bottle, okay, so try to imagine, do you think that the rate of water coming out from your bottle depending on your diameter here or the diameter here or the diameter here? So try to imagine the situation. All right, so it's going to be very, very logical that to understand that it actually depends on here. Okay, let me try to give you an example of, I'm not sure what is this thing called. It's okay, you can try to check that out. Okay, you know, you have something like this in your real life situation that you ever see, you know, this thing, like where you have all the sand, then after that, the sand going out, am I right? So how much the sand can actually go through the other region is based on how narrow is this, right? If let's say it's based on here, then the sand cannot go through. Like this is a common sense, right? So how the sand can pass through is actually based on this most narrow place, then after that the sand coming in. So it's the same thing when we talk about the water as well. So even though you have a larger space here, but then because of you only, this part is much more narrower. So that's why the maximum that you can do is based on the much more narrower region. All right, so I hope that you get what I mean. So that's why when we try to talk about what's the maximum that you can actually allow water to pass through every time, it will be basically depending on our minimum here. So which is going to be the 5 here, the 15 here, and also the 5 here. So you would observe that the rate of amount of water that you can pull out from the bottle at any point of time depends on the most restrictive part of the bottle. So that's why by using this idea, I hope that you can understand and you can connect to the part where why we said that when we find the minimum cut, it will actually equal to our maximum flow. Alright, so minimum cut is the cut will happen at your most restrictive part lah. So this is where you get your minimum, right? Maximum flow is that's going to be the maximum that you can happen in your network. Alright, so that's the part. Okay, now we'll be looking at some question and to understand why do we actually need this, and I'll try to explain it from there. Alright, so all the example that we will be doing here is the example that we did in the previous lesson. So which means we already found out all the maximum flow already. And what we need to do here is to verify that the maximum flow that we find is the correct one by using minimum cut. Alright, so let me try to explain the idea here again, which if you remember from our previous example, right? We say that it's very important to have before I talk about the systematic approach, we say that it's very important for us to have that common sense to select the right path so that you are not wasting the capacity of any edges. So for example, this is the one that we discussed previously. So if you try to go through here, then you can get 40. And when you try to go through here and you can get another 40, which is going to be a total of 80. So the problem here is if let's say you are not selecting the right path, So you want to go through AB, then after that BD, and then here, then which means that you realize that you will be wasting the 40 here and the 50 here, and at the end of the day, your flow here is only 40. But this is actually not the maximum, right? Because we know that definitely 80 is bigger than 40. So this is why we need this minimum cut. So after you find your answer for maximum flow, if you cannot get a cut with the same you cannot get the cut which is the minimum, which give you the same value, then you know that your answer is wrong already. All right, I hope that you get what I mean. Okay, so let's try to do it. So for example, in this case, we know that the maximum flow is 80 unit. So that's why when you try to identify the different cut, you should be able to find out a cut that give you a capacity of 80. If you can't do that, then which means that your maximum flow is already wrong. All right, okay. So there are different way of cut that you can try to do in this diagram. So the easiest one will be here, and then you can see here, or either you can try to draw here or here. So that's the basic law. So you can try to find out. So 40 here. So I hope that is very obvious. So the source region, the sink region. So that's why the capacity here is 80. All right. So when you try to look at this cut, then you have the easiest way to look at it, right, is that you can try to look at your arrow. So A to D, B to D, A, B to C. So you can see all the edges that the cut pass through, right, is basically from the source region to the sink region. So which means you need to add them up together. So 40, 40 and 50. So that's why it's going to be 80, so 130. All right, so the same thing you try to check out here. So when you're trying to look at this, then same thing. So you can see that this is the region from your source. So that's why B is in the sink, right? So when you go from the sink to the source, then BD is not calculated. So that's why 40 and 40, which is going to be 80. And after that here, I think this is very obvious because you can see that the source region and the sink region, right? So 50, 40, that's going to be 90. So that's why when you are trying to draw a different cut, then you can see that the minimum cut that you can find is only 80. So you cannot get an answer which give you 40, right? So that's why if let's say you are using the wrong path just now, then when you are trying to carry out your minimum cut, you will realize that you can't get an answer which give you 40, then which means the answer of 40 is wrong. All right. So, of course, if you want to talk about the much more application part, so, okay, you might be having a question. If let's say I can straight away get this 80, right, then why do I need to use the systematic approach? I can straight away use minimum cut then to find the maximum flow. So the answer is yes, you can. So, but it will be depending on the question, what is the approach that they want to do, lor. But for example, in a lot of question in our exams, right, they will need you to do it by using the systematic approach, which means listing your path. Then after that, write down what is the capacity that you are using then to find your maximum flow, which means what we tried to do in previous lesson. So that's why, although you can get the same answer from the minimum cut, you still need to know how to do the systematic approach because normally this is what you will be asked in your exam. So after you do that, normally what we try to do with minimum cut is to verify our answer for maximum flow. So if you can get a cut with the minimum capacity, which this capacity is totally equal to your maximum flow that you find, then you know that your answer is correct. All right, I hope that is clear. So that's why the minimum cut in this case, there are two answers. So either one that you draw, they are all correct. So which means that this will be your answer. So this is the cut that give you the minimum, which is equal to 80. So that's why this is correct. All right, so let's move on to number 2. Okay, so now the graph will become much more complicated. So you can imagine that you will have much more possibility of creating a cut already. So you can imagine you try to cut it here, you can try cut it here, you can try cut it here, you can try to cut it here, you can try cut it here. All right, so that's a lot of possibility. So that's why you need to identify one by one and see whether you can get this value or not. If let's say you really can't get this, then you know that there's something wrong for this answer already. So if you confirm that your answer here is correct, then which means that you definitely can find a cut which give you the minimum capacity, which is 680. Okay, so let's try to do it one by one. Maybe normally I will encourage you to start off with the easy one, the front and the end, right? So the front part, if you cut it here, 400, 300, 100, so source and sink. So this one, no need to, it's very obvious. So yeah, when you add them up together, is 800. So that's why, all right, so you can imagine that it's not the minimum lah, it's not small enough. If you try to cut it here, 750, okay, then this is smaller than 800 lah. Of course, this is the minimum that we can find just now, we can found now. Then when we move on, so maybe if let's say you want to cut here, so this is still source region, sink region, 450 plus 200 plus 150, that's going to be 600 and 800. That's even more than 750. So you know that the answer is wrong. So when you move on, then you can just try out maybe, I try to cut it here. Yeah, so you can realize that source here and sink here. So that's why, yeah, this obviously is going to be something bigger lah. So 280, 200, 200, that's 680 already. Then plus this one, you're going to have 830. So that's why all these are wrong. Okay, then let me try to give you a tips here. So you can imagine, right, what you are doing here is to find the minimum cut. So that's why this is also common sense that you can try to use. So you might want to find a cut that pass through the edges which give you the minimum weight. I think this is this is very logical, right? If you want to get the minimum sum, of course you are finding the minimum edges for you to get the answer. So if let's say I'm the one that trying to draw different cuts, right? I will definitely choose to start to cut off here. Then after that, I see later I want to cut through where. Reason being is 400, 450 and 600 is going to be much more bigger than 280. So you can imagine when you want to total up with other cut edges, it's going to be something that is not giving you the minimum. All right, I hope that it makes sense. Okay, so now we can continue. Okay, so if let's say this is the one that's minimum, then when you continue, you cannot cut here, right? Then you have your source and sink at one region already. Okay, so now we continue to try out. Okay, so when you want to pass through here, then you can see that, okay, this might be the minimum here. So I choose to pass through here. Okay, then continue. Then I have 150, 210, 200 and 100, and then 150 and 150. So they are both 300. So maybe I want to try out both. So this is one type and this is the other one. Okay, now let's check. So for this one first, all right, so for this one, you can see that the source here and the sink here. So which means that for here, 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 they are all from the source to the sink. So that's why you need to add them up together. So 300, 450, and then that's going to be 730. So this might not be the minimum. Let's try to check out the other one that we draw. Okay, so from here to here is source to sink. This one is also source to sink. All right, and also this one source to sink, and this one also source to sink. So when you try to add them up together, you realize that, hey, the answer seems to be the same, which is not the smallest as well. So 300, 450, and then that's going to be 730 also. So that's why this is not what you want, then we might need to continue. So if you think that it's very messy, then normally what you try to do is I will encourage you to just erase from time to time lah, as long as you cannot. So you just keep the minimum that you can find. So just now the minimum that we remember is 730, right? So which means this answer is wrong. No, it's just that you didn't get your minimum yet. Okay, so same thing, we try to continue to find out the other possibility. So 280 here. So maybe I can choose to, so just now I already passed through here and I already passed through here, right? So the next one that I try to choose is, if let's say I try to pass through here, 300 and then 100. So you have 400 and then plus 280. What is that? You realize that 680. So this is the minimum that you can get already. I don't think you can get much more lesser lah. So even you try to pass through here as well, you have all this number plus together, you wouldn't be able to get what the value that's smaller than this. So that's why this is the minimum cut that verify your maximum flow. So that's why your answer here is just going to be this cut. All right, so I hope that you understand the process. So I try to speak about my thought process so you can understand what I will be thinking when I trying to do this kind of question. then same thing, try to use some of the common sense of numbering that when you are finding the smallest number, what are the approach that you are going to do. But you must make sure that the cut that you are drawing is a valid cut, is not an invalid cut, okay? So after you do it, then you might want to check so whether you have two region with source at one side, then after that sink at one side. So when you total up them together, then it's like a number for, then your verification is correct. All right, okay, so now let's move on to number 3. Okay, so this one we also already get the answer. The answer here is 80. So same thing like what I say, you might want to find out the one that give you the most possible answer here. But I think this question is very obvious already. So yeah, because if let's say you are quite good in method calculation, then you should be quite, I mean, it should be quite obvious. It's actually at the starting here. So 30 25 25 that actually give you 80, which verify this is correct already. All right, as simple as that. So but of course, if you want to try out whether you have other alternative or not, you can also try out as well. So which means, yeah, you might want to, if okay, but then same thing, a common sense here. So okay, I try to talk about the thought process here as well. So the other thing that you can try to think about it is that when you're trying to think of to find out the minimum cut, right? So the first thing, like what I say, to find out the one with the smaller weights. Second thing is to try to find out a cut with the minimum edges that you involve. Okay, for example, when you try to cut here and you try to cut here, you only have 3 edges involved. Am I right? So that's why imagine if you have 5 edges involved and 3 edges involved, of course, the total for 3 edges might be smaller than the 5 edges. So although the 20 here is the smallest value, but it's not going to be very logical. Reason being is you realize that you will pass through more than 3 edges. So you see, 20, 30 is already 50, and you try to go through another here. So that's why that's going to be much more than 80, right? So if let's say you think that 10 and 10, it seems like a very last one, so you try to go through here. Same thing, 1, 2, 3, 4, 5 definitely is going to give you a much more larger number. So 40, 50, 60, and then 85. So that is more than 80 as well. All right, so again, like what I say, please try to use this time to practice your mental calculation. It will be very helpful for you, especially you are trying to do your minimum cut. Because when you look at numbers, it's easier for your mind to think about, hey, what's the total here? Then you can try to imagine whether you can get the numbers or not. All right, so this is for example 3. So this is very straightforward. Okay, let's look at number 4 and see whether, I mean, it's challenging for us to realize the minimum cut or not. All right, so same thing, you can try to start from the front and the back lah. Normally, that's the easiest one to look at. Okay, so the front here, if you cut it here, then you have 250, 150, so 400 and that's 600. Okay, then let's try to look at the back here. You have 400 and that's 500. Okay, so by looking at this value, then you might know that maybe you didn't reach the minimum yet, then we might need to continue. Okay, another thing, okay, this is another thought process. What I will try to do is, when you try to look at the numbers, I'm not sure that whether you can get this or not. You can see that this is 490. By using a common sense, right, you know that all this value 200 with 50 at the end, you wouldn't be able to get 490. I hope that you get what I mean. Because you add up those with 50, 00, 50, 00, then of course at the end of your number, it should be 00 or 50. Since you have a 90 here and this is the only 90 that you have, I mean, I'm not saying about the part if let's say you have all these weird number, yeah. I mean, what I mean like a weird number is like you are not having like a perfect 50 or 50 or 100 here, then it will be harder lah. So in this case, then you can see that this is the only 90. So this is, I mean, it's going to be something, when you try to think of it logically, then it's like 100% that your cut will pass through here. So this is something that I'll try to think about. Okay, then after that, same thing, you try to find it out. So the same, after you cut it here, then you have two choices. So either you cut through here or either you cut through here. So same thing, common sense, 250, then it's going to be 250. If you try to cut it here, then it's over, that's only 100. So that's why if you're finding a minimum, then definitely I'm going to choose to cut through here. So the same thing now, I only have like few choices here. Either I go here, or I go here, or I try to go here. So same thing lor, which one give me the minimum? 250 plus 50, that's 300. So this one also 300. And then this one is 500. So I'm definitely not going to think about this. So let's try to check out for these two different one. Okay, let me try to draw two lines. So this is the first one, then this is the second one. I think both of them may give you the same answer. Okay, so if you try to draw a cut here, then you realize that here, here is where you cut the edges, right? So these are all from the source to the sink as well. So that's why all these numbers should be involved when you try to calculate your capacity. So 250, 50, 300, 390, and then 100. So that's why 490. So same thing here, 200. So this is the source region, then this is the sink region. So that's why all the place that you are cutting here are actually directing the flow from the source to the sink. So 200, 190, 100. So that's why 490. So for this question, you have two answers. And definitely when you try out all the other places, you wouldn't be able to get something that is lesser than 490 already. So this will be our answer for this minimum cut. Alright, so I'll encourage you in your exam, remember to always bring your pencil lah. So especially when you are doing this kind of question, right? So yeah, you might need to do some, drawing in your graph that you might want to erase time to time. So to prevent that it's kind of like looking very messy, right? So that's why try to use pencil lah. Okay, so the two answer here, either you use this or you use this. Alright, please remember that the thing that we are doing here, right, is that either if the question want you to find out two different cut, then of course this will be your answer. Like if let's say you need only one answer, then do one answer. So all the cut works independently. So please do not have the idea where when I draw these two cut, then all the flow already stop here, then which means no flow stop here already, then the cut here is 0. Okay, so remember all the cut works independently. So it doesn't affect each other. So normally when we try to find the capacity, we are looking at if let's say we fit in one cut, then what's the capacity? Alright, so this will be the two possible answer for this question. Okay, so I hope that you can try to spend some time to try out the exercise 6b. And of course, if you have extra time and you think that you want extra exercise, feel free to feel free to verify all your answer in exercise 6b by using minimum cut. So previously we learned how to list down all the path, then after that you find the maximum flow, right? So if let's say all your maximum flow answer is correct, which means that you should be able to find a cut in your diagram that give you the minimum value, which is the minimum cut, then this minimum cut is going to equal to your maximum flow. So that's why you can try this out again with your previous exercise as well. If you need any extra exercise beside your exercise 6b. Alright, so that's basically for today's lesson. So I hope that you can spend time to understanding it, and for next week, we will try to move on for another new subtopic already. Alright, thank you.